Hey guys, in this video I'm going to show you how to implement the elliptical slice sampling algorithm. I have the paper up here by Murray, Adams, and Mackay. It's a pretty interesting algorithm. I like it a lot because of the simplicity it adds to Bayesian inference. This was actually, believe it or not, my very first exposure to Bayesian inference through MCMC. Was through this paper. So I'm going to show you how to implement this algorithm, and let's get started. So to begin with, they actually offer some pseudocode for this algorithm that I'm going to draw on. So I have a empty text file here, elliptical slice sampler.py. I'm going to take an object-oriented approach to designing this algorithm. So let's go ahead and make a class. And I think I'll be using Python 3 sort of styling for this. So let's just add a little doc string here. We can maybe fill out the details a little bit more later, but we'll create an init self. Now there are basically three things that I think need to be included in the constructor or the init method for an elliptical slice sampler class. And first of all, we're going to need the mean, the covariance, and a log likelihood function. And I'll make that explicit by naming it log likelihood func. So initialize parameters of the elliptical slice sampler object. Now you'll notice that these three parameters I think actually correspond to what's described as the input to this sampling function. Now if you notice, they're assuming that you have a normal zero mean and covariance matrix sigma input. But in truth, this algorithm generalizes in a pretty straightforward manner through a change of variables. So I'll include the mean as an explicit input. I'll also include the log likelihood function as well. So self.log likelihood func equals log likelihood func. Good. So the way that I'm thinking that I'll break this up is I'll have one method, which will be a sampling method with inputs and samples, and then we'll have a sort of burn-in time for the number of iterations we want to do before we actually start collecting samples from the elliptical slice sampler. So I haven't implemented that one yet. And then I'll have an internal method which will take in a current state. Now if we go back, we'll see that the current state is denoted by f, so I'll use that same notation. And the output of this function will simply be well, the output of this routine in the paper. So, oh, I see I've forgotten the self keyword, so I'll add that in. So I'll take the current state f. Alright, and from here, I'll add another pass since I haven't implemented that function yet. For the sampling, what we'll need to do is figure out the total number of samples. So total samples, which is just n samples plus burn-in. And I will create a matrix of zeros for now, of size total samples. And I actually need to know the dimensionality of what I'm trying to sample. So in order to get that, maybe I can just do self.covariance.shape 0. And I think that'll do. Okay, and then to return, what I imagine I'll do is I'll just return the samples from burn-in onwards. And I think that works to exclude the first burn-in many samples. Maybe I'll set burn-in to some reasonable value, like 1,000 or something. That may be a little high. I guess it's application dependent. Anyway, so now what should I do? I guess I should just write a for loop. For I in range 1 to n, or excuse me, total samples. Now the reason that I've started at iteration 1 is because I have the idea that when we draw a sample according to the elliptical slice sampling algorithm, we can use that as the input to the next iteration of the sampling routine. So I guess we'll just start with some default value, which will be located in the 0th index according to the rows of the samples matrix. And then we'll just use that as input. So basically what we have is samples I equals self dot underscore sample, and then we'll do samples I minus 1. Seems okay. And then I think all I really need to do is implement the sampling function. So let's do that. What do I need to do? We need to choose the ellipse. So they denote that by the parameter new. So np.multivariate normal, or excuse me, np.random.multivariate normal. And then we'll have self.mean, self.covariance. Okay, and then we need a likelihood threshold. So we need to do log y equals self.log likelihood func evaluated at f plus np.random, excuse me, np.log np.random.uniform. By the way, you'll notice that they say that they actually define this variable u, and that's very much correct. But it's not referenced anywhere else, so I'll just save a step and include that in one line by calling np.random.uniform and np.log. Okay, and then the idea behind the elliptical slice sampler is that you have this bracket that is adaptive, and that is parameterized by a theta max and a theta min, and theta is between the two. So to begin with, theta equals, it was uniform between 0 and 2 pi. We can do that again. 0, 2 times np dot pi, and then we'll just define the theta min and theta max as they describe. Theta minus 2 times np dot pi, and then theta is theta max. Okay. Now, what they describe is basically to iteratively shrink the bracket until you find a point that you can accept according to the elliptical slice sampler. And if you fail to accept a particular candidate, then what you do is go to line 4. You can see that on line 10 of their pseudocode algorithm. So what we're going to do is create a while loop that starts at line 4 and then just proceeds through line 9, and if line 5 is ever true, then we will accept f and or the candidate point and return, and that'll break us out of the while loop. Okay? Now, I'll say fp equals, now here's the thing. They haven't written this pseudocode to account for the fact that you might want to sample from a multivariate normal with a particular covariance matrix, or excuse me, a particular mean vector. So what I've done is I've thought about how you would augment this, and what you do is you shift f according to its mean, and then you'll have to add it back in later on. But first we have to multiply the d-meaned f by cosine of theta, np dot cosine theta, and then we add in nu times np dot sine theta, and then we add the mean back in, self dot mean. Let me just shrink this a little bit so it's more clear that these terms are supposed to go together. Okay, so now we have a log f, well, really log f prime, which is going to be the self.log likelihood function of f prime. And then if log f prime exceeds log y, then we can return f prime, and else we need to shrink the bracket. I forgot the while true. I was wondering why I had an error on that line. All right. Anyway, so if we don't accept that candidate point, we need to shrink the bracket. So how do we shrink the bracket? Do if theta is less than 0, then I think it's theta min equals theta, else theta max equals theta, and then we need to resample theta. So np.random.uniform between theta min and theta max. Okay, I think that pretty much implements the elliptical slice sampling algorithm, untested though it may be. Let's go ahead and start adding some documentation to this. So very helpfully, the pseudocode actually comes with a decent amount of explanatory notes, and of course there's also the full paper. But we can start adding some of our own. So this is an internal function that draws an individual sample according to the elliptical slice sampling routine. The input is drawn from the target distribution, and the output is as well. And in order to get something that is drawn from the target distribution, that's why we have this sort of burn-in parameter. So the first thing is to choose the ellipse. Choose the ellipse for this sampling iteration. Set the candidate acceptance threshold set the bracket for selecting candidates on the ellipse, and then this iterates until a candidate is selected. This generates a point on the ellipse defined by nu and the input. We also compute the log likelihood of the candidate and compare to our threshold. If the candidate is not selected, shrink the bracket, and generate a new theta, which will yield a new candidate point on the ellipse. Okay. This function is user-facing and is used to generate a specified number of samples from the target distribution using elliptical slice sampling. The burn-in parameter defines how many iterations should be performed and excluded to achieve convergence to the target distribution. And that really is an important step. You'll often find that if you don't do a burn-in, then the sampling may not be very effective. Let me okay, so that's pretty much it, guys. I think this code will probably work. I guess we should probably write a test case. Let me edit that, and I will see you guys when I'm done. Hey guys, welcome back. So I've gone ahead and I've implemented a test function for the elliptical slice sampler. What it's going to do is, suppose we have a Gaussian prior and a Gaussian likelihood, and you may know that the product of two Gaussian densities is proportional to another Gaussian density, and that's what lines 111 through 114 show. Then I'm going to draw 10,000 samples using an elliptical slice sampler, and I'll visualize how well those samples conform to the density of the true posterior. By the way, I had two bugs that one bug and one improvement. The first improvement that I decided to make is that the first sample shouldn't just be a vector of zeros. I decided it should be a draw from the prior. So that's the first thing I did. The other thing is I actually had self.mean right here. That's not correct. It needs to be a zero mean multivariate normal random variate, not one with the prior mean. So that was a mistake, but I have fixed that now. And I've gone ahead and added pretty much enough documentation that I'm happy with to this program. Let me go ahead and run it. It takes a moment because we're drawing a pretty substantial number of samples. But you look at it and you think, that looks pretty good for a prior that was just a standard normal, as I recall. Excuse me, it's a prior with mean 1, or mean 5 and variance 1. So still we see that there is some convergence, good convergence to the true posterior in terms of how well the normalized histogram of our samples conform to the true density. So I was quite happy with that. Anyway, guys, thank you very much for watching, and I hope to see you next time. This is Viking Penguin signing out.